Yeah, can begin. So welcome everybody. This week's Majorana-Raychaudhuri seminar series. Today's speaker is Pulkit and from Imperial College London, and he's going to talk about curvature perturbations from non-equilibrium phenomena in the very early universe.
Okay.
I'll send you a reminder when 5 minutes are left.
Yes, great. Yes, thank you. Yeah, thank you, Anish. So yeah, I think first of all, let me thank the organizers for inviting me, and especially Anish. And Right. So and thank you all for joining as well. So today, I'm going to be talking about this. This is sort of a summary of my PhD work, and this has to do with the curvature perturbations from non-equilibrium phenomena in the very early universe. And this is work done in collaboration with my supervisor Arthur Ryan at Imperial and with Bjorn Garbrecht at the Technical University of Munich. So let's just I think we should just start. So see, so yeah, so we know that the two keystones of the standard cosmological model of or lambda CDM are homogeneity and isotropicity. So written in terms of the metric takes this flat FRW form where the scale factor A bar denotes the background scale factor, right? But we know that the universe is not exactly homogeneous and isotropic because, of course, we see stars, galaxies, planets, and of course us as well. So yeah, this constitutes the sort of the large scale structure of the universe, and then we also see from the era of recombination that there are temperature fluctuations, uh, which we see in the form of the cosmic microwave background or CMB. So, so then that means that the universe is not exactly homogeneous and isotropic. And to capture this departure from homogeneity, what we can do is we can treat the we can treat them in the form of perturbations. So here the scale factor is now separated into a background scale factor A bar, and then we have this small perturbation zeta, and then the total scale factor can be written as a combination of the two. And here, so this zeta is the most important quantity in terms of uh, in the very early universe, and it's known as the scalar curvature perturbation. And in fact, why it's important is because it can be directly related to the CMB and large scale structure observations. So so that's yeah. So then once we have zeta, then how do we connect, let's say, our theories of the very early universe with this zeta? So how do we calculate this curvature perturbation? So for that, let's look at this. So there exists a very simple sort of formalism known as the delta n formalism for calculating zeta. So if you so we can divide the evolution of the universe in terms of spatial slices. So that's seen in this figure, and then time threadings through them. So at each time in the universe is can be divided into a three-dimensional spatial slice, and then the slices evolve as time evolves, right? And so what we can do is we can write this evolution in terms of this number of e-folds n, and that is given by a quantity known as the Hubble rate and the integral of the Hubble rate from some slice t1 to some slice t2. And the Hubble rate is defined as 1 over a times dA by dt. But recall that has a background part and the perturbation part. So then if we just separate out the two parts, we immediately see that, okay, we get like a log of the ratio of the scale factors between the background slices. So this is sort of the number of e-folds of the background n bar. And then we have the difference in the curvature perturbation between the two slices. So if we start with a slice which is flat, so zeta equal to 0 at time t1, then we actually obtain this well-known result known as the delta n formula, which is just that the zeta at the final time slice will be equal to the difference in the number of e-folds of evolution between the two slices. So this is how we then can relate zeta to the evolution during the very early universe. And now, so yes, so what is the observable that we want to calculate? So this is known as the non-Gaussianity. So of course, when we make observations of the sky, what we see is temperature and matter in the form of a distribution. So it's like it has to do with statistics, right? So how do we capture the statistical nature of this distribution? So one way is to use this parameter known as the non-Gaussianity parameter, and it's described by this notation FNL, and it's just given by the 3-point correlator. So this is, of course, in momentum space, the 3-point correlator of the curvature perturbation. And then in order to normalize it, we sort of have to, yeah, divide it by the 2-point curvature correlator squared. So this gives us a sort of a dimensionless number, which can then be compared to the observations of the CMB or the large scale structure, etc. So this is a good way to connect the theory to the what happens in the theoretically in the very early universe to the observations that we do today. So yeah, this is yeah, and then I think so. The whole idea is to then calculate what this FNL would be from various scenarios in the very early universe. Right. And one of the most, I guess, well motivated and uh, uh, yeah, well motivated era in the universe's evolution is we believe is inflation, right? So it's an almost de Sitter, so it's an almost constant uh, constant Hubble rate expansion, right? So during a de Sitter expansion, we know that there exists some sort of notion of a horizon, and so what causality basically implies is that the universe can be divided up into separate Hubble volumes, right? So let's look at the picture in terms of the inflationary potential V as a function of some inflaton field phi, which is a scalar field, right? So when the potential is this in this flat region, then then we say that it has a nearly de Sitter like expansion. And so the largest currently observable scale is given by this is denoted by this n star, and then we say that okay, so at some point we choose a point, let's say, which we call some ini point towards the end of inflation, uh, and as we can see, these two scales have a wide separation between them. So typically, the currently observed number of e-folds are, let's say, n equal to 60 or so, and then we'll take this ini point will be the number of e-folds equal to order, so like 5 or so, 3 5 or something like this. So there is a large, so the point is that there is a large separation between these two scales, and so the evolution beyond this n equal to n star e folds, that those modes which exit the horizon before that, they constitute uh, in terms of real space, they are larger than the observable universe. And then the modes from n star to n ini, they constitute they constitute the separate Hubble volumes at n ini. And then the modes which exit the horizon after n ini, that constitutes modes which are shorter than a single Hubble volume. So I think it's better to look at the actual picture in real space. So this is actually known as the separate universe approximation. So essentially what I'm showing in this picture is a snapshot, let's say, we can think of it as a snapshot of the universe at the scale n ini, right? So as I said, so the modes which exited beyond n equal to n star e folds, they constitute this entire universe portion of the universe, and then the modes which exit at the largest currently observable scale. So that A star H star, that corresponds to this circle, which is the observable part of our universe. And then at the scale n ini, the universe can be thought of as divided into these separate Hubble volumes, and each of these so the intermediate scales are what constitutes each of these separate Hubble volume, and the scales which are smaller than this each separate Hubble volumes uh, are part. So they form the the picture which they form the evolution within one Hubble volume itself. So the important thing I think to note here also is that so once we have this picture, let's see how we can populate these separate universes. So let's say we have some so we have the inflaton field, and then let's say we have a separate field known as the spectator field chi, which is also a scalar field. And the main idea behind this approach of the separate universe is that the spectator field chi will have quantum fluctuations at the initial time slice n ini. So its variance would be given just by this is the standard definition of the variance, will just given by the integration of the power spectrum over the range of momenta. And the point is that this variance is actually, we can calculate from the evolution during the inflationary state. So uh, if we include the scale dependence during inflation, so we don't assume that the evolution during inflation is like the Hubble rate is almost constant and the effective mass is small. If we don't assume that, so if we include the full scale dependence, then we find that the power spectrum goes as, so if for a scale invariant spectrum, it would have gone as h square over 4 pi square. But because of this scale dependence, now we have some extra additional damping factor e to the sum, which is captured by some f, which goes from whichever scale we are interested in up to the scale uh, n ini, right? And then the idea is that so because this is a statistical process and we are looking at it in real space, what it just means that the each of the Hubble volumes is populated with a Gaussian probability distribution for the spectator field. So so this is in equation 2, this is the Gaussian probability distribution. And the variance I'm now denoting by delta chi square, and the mean is then denoted by chi bar. So maybe it's helpful to go to the picture again. So the mean chi bar is sort of so from maybe naturalness arguments, we can say maybe the mean over the entire universe should be zero, but that doesn't necessarily mean that the cosmic mean over our observable patch should be zero. So this is an important distinction to make. And what we are saying is that in so when we say that the field develops quantum fluctuations beyond the horizon, in real space, what it means is that in each of these separate Hubble volumes, uh, the field can take a different value depending on which Hubble volume it is in. And but from inflation, what we just get is the distribution of these different field values in different Hubble universes. Sorry, in different Hubble volumes, and that's characterized by this quantity known as the initial variance. And both the cosmic mean and the initial variance we can obtain once we once we know what our inflationary model is. So that's the idea behind the separate universe picture. And now why? So of course, when I said that this is a separate spectator field chi, why do we need us or what's why should like why do we need to separate out that field from the inflationary field? So that's because of a few things. So if we want to have a or if for a scenario to generate large or significant non-Gaussianity that is then observable at the current or future experimental level, what we want to what there are a few ingredients that we require. So first of all, that the field should develop significant fluctuations over the separate Hubble volumes. So what this means is that the field actually should be the mass of the field. Uh, uh, so the first thing that this implies is that the this field cannot be the inflationary field, because in a real space picture, we can always go to a cosmological gauge in which a single field, which is the inflaton field, we can make it uniform in by choosing a uniform cosmological gauge. So that means on top of the inflaton field, we need another field, which is the spectator field, so that it can generate these so different fluctuations over the separate Hubble volumes. And for the fluctuations to be significant, the field should also be light. So the effective mass of the field should be less than the background Hubble rate. And the second sort of requirement is that the field fluctuations over the separate Hubble volumes, they modulate the local expansion of space, because as we saw that the curvature perturbation zeta is related to the delta n, which essentially is the local expansion of space. And that means, so for this to be true, then we need some sort of a non-equilibrium phenomena to take place in the very early universe. So, I mean, examples of such non-equilibrium phenomena are the Curvaton mechanism, in which the spectator field comes to dominate the energy density towards the end of inflation. And then we can have other non-equilibrium phenomena as well. So one of the highly motivated ones is also the phenomena called preheating, which I will describe later on in this talk. And then we can also have vacuum transition in the very early universe, which we also will see later on. So what we need is a light spectator field, and we need some sort of a non-equilibrium phenomena to occur, and then we expect the non-Gaussianity to be significant and observable in current experiments. So how do we now then go from this number of e-folds, so the inflationary theory, which is the delta n, to the observable parameter, which is this FNL. So what's usually done is we can simply expand the delta n function in terms of the mean and the fluctuations of the field. And yeah, I'm skipping over the step in the calculation, but what we find is that FNL is just given by the first, so it just depends on the uh, on the power spectrum of the field divided by the observed curvature power spectrum and the derivatives of this function delta n. So this is how we then can directly relate the evolution during inflation with uh, the observable quantity FNL. So that's sort of uh, the sort of the method which we will employ to to extract some observable data from our theories. And now what I want to do is actually look at this, what I said. So look at specifically at the non-equilibrium phenomena of vacuum transition. But before that, just uh, as a light-hearted note, uh, so so the so the claim so the claim here is, or the picture we want to actually look at is sort of saying that the universe is like an ice cream. So uh, just to just to think about this, so how is ice cream made, right? So uh, it's the answer is uh, with three main components. So the air, water, and milk, right? And what happens is that when the temperature is reduced, uh, the milk particles or the lactose molecules uh, modulate the freezing point of water at different locations in the ice cream mixture, and then this results in different locations freezing at different times. So we form these ice crystals that that form at different times, and then those percolate with air gaps in them, which is actually what gives ice cream its fluffy texture. And okay, so how is this relevant to our scenario? Turns out it is very relevant. So I will go through the scenario, and then I will leave for you to figure out how it's relevant. But it sort of exactly captures what happens in our case. So the the phenomena which we want to study is known as vacuum transition, or or first order phase transition. So I guess the first hint is that water freezing is a first order phase transition as well, right? So so let's say, yeah, so let's describe how would we describe first order phase transition in quantum mechanics, right? So we have if we have a potential which looks something like this, so it has a non-trivial minima and a local minima, and then it also has a global minima. And the local minima is known as the false vacuum, and the local minima is the true vacuum. So classically, of course, we know that this field cannot tunnel through the barrier, but quantum mechanically that's allowed. And of course, we can also describe this in field theory as well. And the picture in real space looks something like this. So we have a false vacuum background, but then we have this tunneling takes place through nucleation of bubbles of true vacuum, which are nucleated and then they expand uh, almost at the speed of light if it's in a vacuum. So if there's no, there are no other fluids present, so then it expands almost at the speed of light and then percolates and then completes the transition from the false vacuum phase to the true vacuum phase. And one of the useful parameters to which characterizes this transition from false to true vacuum is this percolation parameter P, which is just given by the decay rate gamma divided by the Hubble rate to the power 4. So what it essentially is saying that, so percolation is completed when P becomes 1. So what it means is we have, so one bubble forming per Hubble volume per Hubble time during uh, during the very early universe, and that's what we'll take as capturing the for the decay to be complete. And so during inflation, what we can also do is if we have two different fields, so one field is the inflaton background, and another field is the one which is undergoing phase transition. Then we can make the percolation parameter dependent on the background inflationary value. And turns out that this is a good thing to do, because then for people who are familiar with this graceful exit problem during inflation, so having two different fields is what allows us to sort of uh, mm, go beyond or take care of the graceful exit problem. So right, so I guess so then the idea behind calculating non-Gaussianity in this scenario is again the same. So we introduce a light spectator field chi, and so assuming it has a near scale invariant power spectrum during inflation, then it has significant fluctuations over the different Hubble volumes. So let's say we can also just quickly estimate that. So the variance delta chi square is just given by the integral over the power spectrum. And in scale invariant assumption, the power spectrum is just constant h square by 4 pi square. So that drops out of the integral, and then we just have an integral over k, 1 over k, which just gives us the number of e-folds, the currently observed number of like the largest observed e-folds, so n star. So that's around 60 e-folds. So we can directly estimate in this way what the variance of this distribution would be. And now comes the main idea is that in each of these different Hubble volumes, the field takes a different value. And that means that the decay rate, which can also which then depends also on the spectator field chi, is different in these different Hubble volumes. So uh, in each Hubble volume, the percolation, so the decay completes at a different time. And that means that before the decay completes, each Hubble volumes expands slightly differently from the next. And it is this slight difference in the expansion during inflation that leads to that modulates the expansion, and then it leads to a large non-Gaussianity through the curvature perturbation. So this is the sort of the main idea behind behind this work. And so yeah, so this is the overall idea. But then in order to separate out the different components, so we have an inflationary background, then we have a transition sector, and we also have like the spectator sector. So I mean, in principle, they can be the same, but in order to isolate each of the how each different sector behaves, what we will do is we will consider a setup in which we have the total potential, let's call it W, which is a function of three different fields, just for illustration purposes. So one field is the inflationary background inflaton, then sigma is the decaying field, so it has a true vacuum sigma TV and the false vacuum sigma FV, and then we also have the spectator field chi. And so potential which we can consider is motivated by the Higgs inflationary model. So in this, so we just have a lambda phi to the 4 potential where phi is now the Higgs field, and we have this non-trivial non-minimal coupling term to gravity, and we have this sigma sector which is sort of like a yeah which is the transition sector. So the potential is written in a way in a quartic form, so it has a false and a true vacuum. And then the spectator sector is coupled to the transition sector in this way. So yeah, I mean this looks a bit ad hoc, and it is, but yeah. So the point is we are trying to motivate uh, how this scenario can lead to large non-Gaussianity. And if we want to be concrete with the model, then yeah, as we said, so we can fix the inflationary sector to be Higgs inflation. So then the lambda parameter gets fixed from uh, let's say the LHC observations, like particle physics observations. And then also due to the mm, that's to maintain like the tensor to scalar ratio observation, we also can fix the non-minimal coupling value to some very high value for in the case of Higgs inflation. And the point is that the effective mass goes as so lambda phi square. So the effective mass of the field plus lambda phi square plus the coupling between the the transition and the spectator sector. So what this says is that okay, so let's look at how the evolution will go. So when the field value is high at the beginning of inflation, then the effective mass is low. So then we won't have a false vacuum. But then when the when the when the inflaton field value decreases, then we have then the transition is favored, and then that's how the transition will occur towards the end of inflation. So this is just to ensure that the transition occurs when in the observable number of e-folds, because if it occurs very early on, then we won't be able to see its signatures. Right? So yes, and then how do we then relate this to, to the calculation of the non-Gaussianity parameter FNL? So during inflation, we know that especially in slow roll, we know that the delta n is just given by an integral of the potential divided by its first derivative, going from the currently observed scale phi star to the end of inflation phi end. And what we say is, okay, so this is within one Hubble volume, and then within one Hubble volume, what we say is, okay, at the transition phi t, what we let's assume that it's a sudden transition. So the value of the field sigma, the transition field, just shifts. So from phi star to phi t, the value is sigma fv. So the field is in its false vacuum. But after the transition, the field suddenly shifts to from phi t to phi star. It shifts to its true vacuum. And so this is so we separate out the evolution into two. And then what we need, recall that the FNL is defined as the derivative of the delta n, and but we can directly take the derivatives, right? Because this, even though this is an integral, but it's easy to take its derivative. And so the derivative of the first derivative then is just given by can just be expressed in terms of the derivatives of the potential and the derivative of when the transition occurs as a function of the spectator field. And similarly, the second derivative can be expressed in this way. So now, yeah, so now we have reduced the problem to just finding out what the so when the transition occurs in each different Hubble volume as a function of the spectator field value in that Hubble volume. And that we can also estimate quite easily analytically through uh, the percolation condition. So this is just the condition that the decay rate gamma is equal to the background Hubble rate to the 4. So the percolation parameter is equal to 1. And if we differentiate this equation, we can just immediately get how the phi, what the transition time in each Hubble volume, how it relates to the effective mass of the action, or the yeah the Lagrangian which we were considering. So yeah, so bringing all of this together, so what we have is, so yeah, so the I mean the main thing to note is we didn't really have to, specify any potential. So this sort of analytical method will work for any potential. And if we bring all of these ingredients together, then starting from a generic potential W, we can analytically estimate what non-Gaussianity we can have. So this is a very good way to to sort of um, uh, constraints beyond the standard model theories which undergo phase transition during inflation. And of course, uh, what we want to, so let's say we want to have some actual numbers out of it. Then what we can do is, so let's say we want to study it for the Higgs inflation model. Uh, and this is a nice little result. So this is sort of a bit of uh, a tangent, but yeah, this is a nice result which we found, which is that for some specific values of the model parameter. So in fact, when the Hubble rate is more than the effective mass, then the Hawking-Morse transition is the one which dominates. And for the Hawking-Morse transition, we can show for a quartic potential that the Hawking-Morse transition actually never completes during inflation. So that essentially means that, yeah, we just get rid of half the parameter space. So we only need to look at uh, so we only need to look at the parameter in which the effective mass is less than the Hubble rate, and so these are known as the Coleman-De Lucia type instantons, or the Coleman-De Lucia type transition in de Sitter space. And this can be, so the decay rate for this Coleman-De Lucia transition can be calculated by using a shooting algorithm. So yeah, I'm skipping a lot of steps here, but I think the main, like, if you want to look at just how the cosmological evolution behaves, so we can capture this by how the so this plot shows how the percolation goes as the number of e-folds during inflation. So we can see that it's small when at large number of e-folds, but towards the end of inflation here, around some 3.75, what we find is that the percolation parameter becomes 1. So that's when the transition uh, that's when we take the transition to complete. And based on that, we can, so we have an analytic formula for FNL, right? So we can just uh, go through, so we can just choose some parameters in our for our theory, and then we can actually, I mean, it's, yeah, what I want to say here is that we can actually put constraints on the parameter. So this plot shows, it's a contour plot of FNL uh, as a function of the cosmic mean, and so as a function of the spectator sector parameter. So the cosmic mean and the cosmic mean on the x-axis, and then the strength of coupling of the spectator sector with the other sectors. So that's denoted by the coupling GS. And what we can see here is that so based on current uh, observations of the non-Gaussianity, this white region of the parameter space is immediately excluded because it has very high FNL, which we don't observe. And then in the near future, the FNL which we can observe will lie in this shaded gray region, and then the black region is uh, is sort of an FNL which is quite low, so it might not be observable in the near future experiments. But the point is that we can immediately put constraints on our beyond standard model theory based on observations of the non-Gaussianity. So that's a very good uh, measure to have. So yeah, so this is sort of the motivation behind this work, is to, yeah, so to actually constrain let's say vacuum transition based on non-Gaussianity. And okay, so as you can recall, uh, so this was one of the non-equilibrium phenomena that we wanted to look at. But another non-equilibrium phenomena that we wanted to look at was the phenomena of preheating. So let's just quickly go through that. So what's preheating? So okay. So sorry, this is a busy slide, but let's first look at this potential picture, right? So during inflation, we have a almost flat uh, potential. Sorry, and then so at some point inflation ends, and then so slow. This is let's say the slow roll ends, and then the field picks up momentum, and then it starts to oscillate at the bottom of its potential. And so this after the end of inflation, this sort of oscillatory era is known as reheating. And so it can be divided up into different sort of epochs. So so when the field oscillates, so the background inflation is oscillating. Uh, if we have another field present, so a spectator field, so this is given by this kind of potential. So we have a lambda phi to the 4 potential for the inflation, and then it is coupled to some spectator field. So this can be a dark matter field or any of the standard model fields, etc. So that's the spectator field chi. Uh, and so so when the background inflaton oscillates, it can actually exponentially generate these daughter particles chi. So that's known as the parametric resonance. But because the equations of motion are nonlinear, the these there will be some backscattering, back reaction and rescattering, and so essentially the exponential growth will stop at some point, and then we will have some also have some turbulence, and then some thermalization, and then finally the universe will exit into Big Bang nucleosynthesis, and then the rest of the evolution of the universe will take place. So this in total, this whole era of the evolution between uh, inflation and Big Bang nucleosynthesis is sort of, we can term it as this thing called reheating. Okay, so this is just a quick summary of reheating. And why why do we want to study preheating? Is because for many inflationary models, so let's say even the scale dependence, or uh, uh, the parameter, or the scale dependent parameter ns, or the tensor to scalar ratio, or the non-Gaussianity even, is proportional to the slow roll parameters. And the slow roll parameters are, because it's a slow roll, they have to be very less than 1. So just based on non-Gaussianity, it's difficult to distinguish which inflationary model actually describes our universe. So then the idea is that, okay, so if instead of that, what if we look at the non-Gaussianity from preheating instead, so after inflation has occurred. And it it has been shown that in this massless preheating, so in this sort of potential, uh, simple potential, it has been shown that it can generate, in fact, large non-Gaussianity, which can be detected in current experiments. So essentially, preheating can then allow us to distinguish between different models of inflation, and that's the idea. And of course, I mean, if inflation is the, yeah, it's the most well motivated, and if it's correct, then of course uh, you have to have reheating, right? So the inflaton has to decay into the standard model particle. So it is um, an integral part of the evolution of the universe. So then we have to study reheating, right? So, or reheating in general. And so, okay, so this is so this is another fun slide. So this is just sort of an advertisement. So of what just to motivate, since yeah, the last part of the talk is that what I what I'm trying to say is, okay, if you have some model of inflation, uh, then if you follow the method which I will describe, then we can calculate what the
Hey, we have 5 minutes left.
yes, thank you, yes, thanks. Yeah, so then we can calculate what the observable non-Gaussianity would be from that. So of course, as any good advertisement, it also has some terms and conditions apply. Yeah. So what are these? So let's just quickly go through them. Uh, so so one thing, which, because the evolution during preheating is highly nonlinear, what we need is we need to actually do use lattice simulations. And so when the essentially the separate universe picture that we saw, what we do is we run a lattice simulation for each of these different Hubble volumes. So we have some very high 10 to the 4 Hubble volumes, and then the delta n as a function of the field looks something like this. So it has like a spiky pattern. So it's sort of non-perturbative. And so we can't really use the standard Taylor expansion of delta n. What we need to do is uh, we need to um, we need to go beyond the standard perturbative treatment, and there is a well-defined way in which we can do that. But I think maybe I should skip this and because of the time. Uh, so essentially what we need to develop is this non-perturbative delta n formalism, and the leading order term in that is proportional to this coefficient tilde n chi. But if we look at the so that depends on but if we look at this again, this delta n function, if our mean of the observable universe is non-zero, then this coefficient delta n tilde this n tilde is non-zero, so everything is fine. But if the mean of the universe is zero, then then this coefficient is so then this integral is antisymmetric. So in chi goes to minus chi, and so this coefficient will become zero. So essentially all the order coefficients will become zero. So what we then need to do is sort of go to the next leading order, and that's we can calculate that, and that's given something like this. So now this depends on the second. So it's tilde n chi chi, and right. So this so yeah. So what I want to say here is that in a scale invariant treatment, we would have assumed that the power spectrum is constant. So that would have given us an FNL which would go as log. Uh, but if we take into account the full scale dependence, then we will get an FNL which goes as a power law instead. And this actually results in a very high uh, difference in the magnitude of the estimate for FNL. So if we if we take some, let's say, if we apply this method to a alpha attractor type model, uh, won't go into the details. Maybe I'll also skip this. So what we find is, so yeah, we when we plot the FNL as a function of the the coupling strength between the inflaton and the daughter field. So what we find is, so first of all, a scale invariant approximation will give an FNL which is order 10 to minus 9. So almost that's very low. Uh, but if we include the full scale dependence, then sorry. So the scale invariant approximation will give an FNL which is order 1, which is observable. But by including the full scale dependence, what we find is that it actually reduces very, very significantly. And so so including the scale dependence is very important. And then what we also
Hi,
see.
we have 1 minute left.
Yes, yeah, thanks. Yeah, no, yeah, I'm just done. Yes. So, yeah, so this is the last slide, in fact. What we also see is that when we scan over this parameter g square over lambda, what we find is that the um, so so for the parameter equal to 2, we were getting 10 to the minus 9, but for 1.6, something like this, we are getting 10 to the minus 4, FNL is 10 to minus 4. So there is also a significant order of magnitude change, even if we consider the full scale dependence. And so I think the main conclusion here is that this shows the importance of lattice simulations, because in order to get to scan over these parameter ranges, we have to use lattice simulations, and those can significantly impact how much non-Gaussianity we expect from preheating. So I think so yeah, so this was all I wanted to say. I mean, the current value of non-Gaussianity is consistent with zero, but the hope is that the sphere experiment, which is now on, which will bring it to less than one, and so hopefully we will have uh, some way to then either constrain these non-equilibrium phenomena of vacuum transition or preheating, and give constraints on the parameters of the theories which have those. So yes, so with this, I thank you for your attention, and yeah, I'm happy to take any questions. Thank you very much.